Yeah, in another 30 seconds, we'll go live.
Yeah, you will share for each one, right? Then
The presentations, ma'am?
that's right.
Ladies and gentlemen, welcome to one of the hottest topics in machine learning today, which is Explainable AI or XAI for short, at the Responsible AI for Social Empowerment, RAISE 2020. And I, Sanjay Bal, am your host for this session. Today, AI-based systems are finding their way into a broad range of industries, ranging from finance, education, defense, healthcare, manufacturing, law enforcement, cybersecurity to autonomous cars and drones, for making and supporting various profound decisions and predictions, including those impacting the quality of life of human beings. The question is, how much do we trust these AI-based systems? Do we know in a transparent manner how and why these AI-based systems come up with the decisions and predictions that they output? Let me take an example here to explain the risks. About 37 years back, the Soviet early warning satellite system detected 5 US nuclear intercontinental ballistic missiles, ICBMs, launched at the Soviet Union. The Soviet watch officer believes that the US launching only 5 missiles in a first strike doesn't make sense. The officer at this point of time has incomplete information and compressed time to make a decision. The officer decides to go with his gut and reports that the system is malfunctioning. The officer was right. The Soviet satellites were falsely detecting sunlight reflecting off cloud tops as ICBM launches. What would an AI-based system have done? Whatever it was programmed and taught to do. AI-based systems would fail to have the requisite capabilities for making discriminating and proportional risk behavior-based decisions as required under international humanitarian law. The responsibility of decision-making would need to lie with various stakeholders, such as users and decision makers who are or will be using these new technologies in their respective domains, scientists and builders who develop these new technologies, political authorities and enterprises that commission the new technologies. States have an obligation to ensure the use of new technologies is consistent with the rules of humanitarian law. Civil society should report on the consequences of these new technologies and have a debate about their legality so as to shape real international public conscience. To ensure that users have trust in AI-based systems, there is need for explainability at the business and industry risk perspective, model perspective, technical architecture and design perspective, regulatory perspective, evaluation and graded interpretation perspective, while ensuring that security and privacy of the system is maintained, thus making the system trustworthy and usable in a wider socio-technical context. To discuss these issues, we have today a very distinguished panel. And let me introduce the panel to you. We have a keynote by Ms. Lan Guan. Lan has deep expertise in all aspects of business transformation powered by data analytics and AI. This will then be followed by our moderator for the panel speakers, Arati, and Arati leads the artificial intelligence capability at Accenture's Advanced Technology Centers in India. She has over 23 years of experience in the field of machine learning and data science, developing AI and predictive software solutions. The panel is Rohana Pala, who has over 15 years of experience in envisioning and deploying machine learning solutions in e-commerce and financial industry. Vishik, who focuses on hardware security, trusted computing, privacy enhancing technologies, some aspects of encryption and related policy issues. Rushi Bhatt, experienced in large-scale data mining, statistical modeling, social network analysis, user-click prediction, and developing novel, adaptive, self-organizing algorithms. Anand Rao, who is the Global Artificial Intelligence Lead and co-sponsor for the AI Center for Enablement within PwC, and the Global Lead for AI, is responsible for research and commercial relationships with academic institutions and startups, research, development, and commercialization of innovative AI, big data, and analytic techniques. We have Srayanta Mukherjee, who is a computational biologist and data scientist, having extensive experience in machine learning methods, regression, classification, and information retrieval. Vineeth Balasubramanian, an associate professor in the Department of Computer Science and Engineering, and currently also serves as the head of the Department of Artificial Intelligence at Indian Institute of Technology, Hyderabad. He also serves as the secretary of the Association for Advancement of AI for the India chapter. Thomas Dietrich is one of the pioneers of the field of machine learning and has authored more than 190 refereed publications and 2 books. He has invented important reinforcement learning algorithms, including the MaxQ method for hierarchical reinforcement learning. He is the past president of the Association for the Advancement of AI and founding president of the International Machine Learning Society. And that will then be followed by a talk by Kaushik Roy, who has worked on the FPGA architecture development and low power circuit design. With this, I'm going to hand over to Arati to take the session forward. But before I do that, it is over to Land to give the keynote address. Thank you.
Hello, everyone. I'm Guan from Accenture's Global Applied Intelligence Practice. Thanks to the RAISE 2020 committee for offering me this wonderful opportunity to speak in this segment about the incredibly rich topic of explainable AI. Let me start out with a story that I think will help illustrate the significance of this topic. Like many of the people who work on artificial intelligence, I have always been a quantitative thinker who is most comfortable dealing with hard numbers and facts. So when I was first starting out on my career and decided on a path as an enthusiastic PhD student 20 years ago, not surprisingly, I chose the field of computational statistics. I thought that picking a highly technical discipline would prevent me from having to deal with the tricky business of explanation and interpretation all day long. Numbers, to someone like me at that time, seem like they are quite black and white. There's always a wrong way to solve a math problem and the right way. So I thought that specializing in a field like statistical engineering meant that I could bypass the sticky, uncomfortable ambiguity of interpersonal interactions. However, my experience working with leading companies in AI arena on behalf of Accenture in last 15 years has led me to the exact opposite outcome. Guess what? I spend every single day working with my clients, dealing with people, not just impersonal machines and algorithms like what I expected. This is because AI is not a cut and dry matter of hard numbers like Dr. Sanjay was pointing out. What we have found is that, in fact, AI requires human insight in order to be effective at all. And in this keynote, I want to share my perspective as the spur to induce our distinguished panelists to come forward with their valuable contributions on the topic, using an ancient Chinese idiom, to attract jade by laying bricks. So these days, as Dr. Sanjay pointed out, AI is woven into the very fabric for our society. It touches on almost every single aspect of our daily lives and is becoming increasingly important in a huge range of industries. Its incredible computational power can resolve even the most difficult business challenges. So does that mean that all of our problems are now solved? Is it time to simply deliver ourselves into the all-powerful hands of AI? The truth is that AI is not a silver bullet, eliminating the need for human intervention. That's not the case. To the contrary, human intervention is even more important than ever in a world of AI, for one simple reason. The black box nature of some AI systems giving results without a reason, without explanation, is hindering the mass adoption of AI. Okay, so that's such a powerful statement. So let me unpack that a little bit for you. As we all know, AI learns from itself by crunching huge data sets, far beyond the capability of any human can do. I know we have a panel of 12 different experts, who can talk about this all day long. But for this very reason, we often have no visibility into how exactly deep learning arrives at its results and conclusions. In other words, the learning process is kind of opaque. Let me give you two examples to show you what I mean. The first example is related to all of us, personal finance, okay? So these days, not surprisingly, many banks are using AI algorithms to decide whether to give you or I, a loan or not. So you might start by comparing the loan amount you requested with your income. Then it might look at your credit history, marital status, or age. Then it might consider any number of other data points. After exhausting this, what I call the decision tree of possible variables or attributes, the computer will spit out a decision. And given millions cases to consider, a machine learning algorithm will tweak itself, until it is able to handle a wide range of novel situations and reliably predict how likely each loan is to default or not, will I get a loan or not. But the problem is that as ordinary humans with very limited computational ability, we simply aren't able to follow along with this machine learning process, this learning process. The final result is that the algorithm spits out is a product of an opaque process. And when it comes to such an arena as sensitive and important as personal finance, many people might understandably become hesitant, at blindly following the orders of an algorithm that they can't even understand. So that's our personal example. Now, my second example illustrates the huge stakes and life-altering consequences that can hinge on AI algorithms. This is a little bit more recent. Okay, so this is a more specific case study about how we at Accenture helped a global tech giant distribute millions of dollars worth of grants to minority-owned business here in the United States. So a little background of that. In light of the recent protests against racial injustice in the US, everybody has seen that on the TV, the tech giant client wanted to allocate $100 million specifically for minority business owners. The program was so well-intentioned, but when this client started looking at the variety of minority business across the US, there are only a couple million of them, it became pretty clear they needed a concrete plan to help them distribute this large amount of fund, to business that were in dire financial situation because of COVID. The threat that the pandemic posed to this business was staggering. 41% of Black-owned business in the US shut down between March and June this year. That is twice the failure rate of non-minority business. Furthermore, many minority-owned businesses are, as expected, are heavily concentrated in cities, urban areas, hardest hit by the virus, and they enter the pandemic with much weaker financial conditions. For all these reasons, the tech giant's primary concern was dispensing the grants as fast as possible to put money in business owners' hands, right, who are in need of financial assistance the most. So naturally, they turned to AI to identify the business that were most in need and get them relief quickly. But this also generated a further question. What were the criteria that the AI algorithm was using in order to pick out this business, to prioritize them? Because of the opacity of AI, without something like explainable AI that we're talking about here, it was impossible to say for sure. Please go to the next slide. I hope these two examples has illustrated for you today's central AI conundrum, right? Which is that where all these tools, all this learning are incredibly powerful, they are also notoriously opaque. Okay, so this presents a problem when AI is being deployed as a solution in the most intimate and personal realm of our daily lives, that example that I was talking about. Why should we trust AI to make such important decisions on our behalf when we can't even understand why it produced the solution that it does? This is the question in millions of people's head, okay? This uncertainty and anxiety surrounding AI's opacity, of course, is very understandable. It presents a formidable obstacle to the widespread adoption of AI. In fact, according to an annual survey done by Accenture, more than 85% of CEOs, they agree that for AI-based decision to be trusted, they must be explainable. So is the lack of explainability the end of the AI boom? In other words, before business can harness the unprecedented power of machine learning, we need to reassure them that AI can be trusted. And this is exactly the function of what we call explainable AI. It's essentially a solution, right? It's a collection of solutions that enables us to answer the pressing question that companies always ask: why did AI system make a specific prediction or decision? Why didn't the AI system do something else? How can the AI system correct errors that arise with confidence? Because it has the power to answer these questions, explainable AI secures the trust of key stakeholders and facilitates the widespread adoption of machine learning. Let's go to the next slide. So how exactly does explainable AI overcome this kind of obstacle? There are several different strategies that it can take, right? First, there's what we call model induction, or the simple observer approach, where an external observer tries to make inferences about how the AI system is reaching its decision. For example, if we want to understand how a neural network recognizes a picture of a dog, we could carve up, instead of just treat that as a black box, right? We could carve up a picture, right, and feed them into the neural net individually. From there, we could also make inferences about which individual parts, the body, the tail, the ears, the fur, right, etc., 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 led to the AI, right, led AI to its conclusion instead of treating that as a black box. So the trade-off that is, of course, it's slower, right, but it gives us more ability to explain what's going on there. There's also what I call the algorithmically surgical approach, where we actually use that quite a lot in our client projects, and I know Dr. Arati will be doing some demo at the end, right? Where we have basically one neural net observe another one. As one neural net makes prediction, the other, what I call the explainer net, simply watches and learns how it makes those predictions. I mean, that's a pretty visual way of describing how they work together. It can then translate those enigmatic, mysterious process into a somewhat explainable format for a human audience to comprehend. So I won't spare you any more further details. I think that's what this expert panel is about, right? Next slide. Let's go to the next slide. So I want to switch topic a little bit. Let's take a look at what this all means in pandemic. Whatever strategy and explainable AI choose to deploy, the fact is that explainability is more important than ever during COVID-19 pandemic. I believe because COVID has produced an unprecedented disruption in terms of the historical data that can be put into the AI algorithms. It's not a surprise. Machine learning models that have been trained on normal, behavior are now showing cracks. Right? There is simply no precedent for the enormous changes in consumer behavior that we're seeing during COVID, which throws a wrench into AI effort to make prediction. For example, airline. Let's switch to the airline industry. COVID has upended everything airline knows about pricing. Demand patterns, booking patterns have transformed dramatically. Not only that, any information about the mix of business and leisure bookings is no longer relevant. AI algorithms struggle to adapt to an unprecedented situation that they were never prepared for. Similarly, right, if we look at the online streaming services, we all heard that they're booming, right? But now they are having problems with their recommendation algorithms because massive changes in subscriber data and behaviors are making these recommendations less accurate and helpful. Now, what we have found is many of the problems with machine learning models arise because more businesses are buying ML systems in haste, but lack in-house know-how needed to maintain them. A crisis like COVID pandemic means that AI systems have to be retrained, which requires expert human intervention. In return, the role of AI augments humans' role, not completely replace it. And I think that's just another angle that I want to call out in light of a pandemic. So furthermore, the problem of how to secure trust in AI will not end with the pandemic, as expected, right? This anxiety around whether we can trust AI has penetrated the public consciousness, and that must be at the forefront of any business strategy involving AI. For example, from regulation standpoint, in 2016, the European Union officially codified a legal right to an explanation of decisions made by algorithms. This speaks to the increasing demand among both business leaders and the general public for accountability, transparency, and explainability for AI solutions. As the simple principle that is unveiled on the next slide, let's go to the final slide. I will close with one final reason as to why this is so important. I think that every single one of us, remember the example that I showed earlier, right? I think that every single one of us here remember doing show and tell as a young student. It's a big thing here in the US, for the grade school, right? Show and tell, show and tell. We're called upon not only to show something interesting, but to tell and to explain why it matter and how it work. In my younger years, as a statistician, I probably would have resented this assignment and failed to understand why the telling part was so important. But now, thanks to my experience with explainable AI and some of the wonderful work my colleague has done, I understand that a technical solution, no matter how brilliant, simply will not be useful if you cannot illustrate what it can do in relatable, understandable terms. Luckily, this is exactly what explainable AI is designed to deliver.
Thank you so much.
Arati, back to you.
Thank you so much, Lan. That was a great introduction and really set the stage for why we are talking about explainable AI today, right? What is the importance of explainability in AI solutions, and how as these solutions are getting more and more pervasive in our lives, building the trust and transparency and having accountability for what decisions they make is extremely important. And I'm really honored to invite the panel that we have today. We have a set of distinguished speakers. Dr. Sanjay has already introduced them briefly. And so I will be directing some initial questions to them, but if the audience has any questions that they would like to ask the panel, please post them, and we will try to take a few questions from the audience towards the end. And so before we start the discussion, I'll just highlight sort of an interesting paradox with explainability. So explainability as a concept is not really new. When credit risk models were being used to make decisions on credit card applications 20, 30 or more years ago, there were regulations in place to have reason codes to make sure that they were not using gender or age related features. But at that time, it was much easier to introduce explainability because typically these were linear models. And so you could easily know whether there were features that were discriminatory in any way. However, as we have improved our AI systems, our accuracy has gone up. We have introduced more complex algorithms. We are able to process a lot more complex data. With that, our performance has improved, but our ability to explain has also become more complex. And that is really the reason that this field now has become so important and so crucial, because as we build AI solutions across the board for every different type of application, being able to explain the reasons why the system is taking a particular decision is becoming more and more critical, as Lan illustrated so well. So with that, I will ask our first speaker, Rushi Bhatt. He has worked on, various text-related applications, job matching related applications. And one of the concerns with AI typically is bias that can be introduced into AI solutions through either the data that is being used or the way the models are trained. So Rushi, explainability and bias have, quite a strong connection. Can you talk about your experience in building models and, how one can take care of this issue?
Right. So I think there are speakers who are far more experienced just in this panel. So how is really still a developing field. There's a lot of literature that is still coming out. A lot of work has already been done in detecting bias, detecting just biases due to the data versus what the model has been given as existing assumptions and so on. I think more than that, there is really a whole system of things that have to go right? So explainability is really just one of the building blocks. Another building blocks, like you pointed out, is also detecting the bias and the sources of those biases in how we train the model. But it all rolls into what's collectively now called FATE in ML, like fairness, accountability, transparency, and ethics, the way Lan also mentioned in her talk just now. So once we figure out how to explain what decision was made, maybe per instance or for a group of instances based on the gender or the location or the race of the individual, if you're talking about individuals, or economic opportunity, especially, which is what I used to work on at LinkedIn most of the times, then these things are critical. One of the things that happens when we start talking about detecting bias in machine learning is we immediately fall back to group level biases. A lot of the laws are also written for group level biases and how some set of people based on reasonably simple features have been wronged, right? But sometimes we forget about the individual instance level misclassifications that can be tremendously destructive to an individual, and that's how probably when we start explaining instances and how those went wrong, that's probably the most powerful way of discovering or diagnosing problems. And I mean, you can see that even in charity appeals, right? So you show a child who is not doing very well or who needs help. You don't show a group of people and so on. I mean, those are when you show an individual, those are the most powerful messages that we can create. And there are several other instances if you go out and look in the news. So that's where instance level explainability and how that relates to the whole enterprise of fate in ML. That's probably where, as machine learning, applied machine learning researchers at least, we should start focusing our attention to. Now, what's being done about it? There are several libraries that are available right now, even in the open source, right? So LinkedIn itself, a couple of months ago, they open sourced a library called Lift, which is really a model agnostic way of detecting and quantifying biases per group or per combination of variables, and that can tell you whether the system, the model is systematically doing better or worse for certain groups of input data, right? There is other stuff to be done as well. So one of the other up and coming areas where Professor Dietrich has also worked in the past is on identifying out of distribution instances where the model can systematically go wrong and confidently can go wrong, right? That's the other area where attention is needed. So I'll stop there.
Thanks, Rishi. I like the word confidently can go wrong. I think even we humans do that sometimes, and I think we have to teach AI systems how not to do that. But you brought out a very interesting point, the explainability at a model level versus at an individual transaction or outcome level. I think those are different and need to be used for different purposes. And we can explore that a little more through the upcoming discussion. So my next question is to Rohan. Rohan works at Amazon. Lan touched upon how COVID-19 has impacted in terms of analysis and modeling, because historical data in some ways is not as important. But another way COVID has really impacted us is in terms of our dependence on online deliveries. So Rohan, I think you have some interesting example of how you've used explainability in some of the models that are used in that process. So can you share some examples with us?
Sure. Thank you, Arati, for that question. And I want to thank Ray's committee for giving me the honor of being part of this panel. It's just a fabulous panel. If I can have the slides, please. Perfect. So just let's stick on the slide one, please. So I think I'm going to talk briefly about Indian addresses, and that's where we used explainability tremendously, and we kind of pivoted the ML frameworks in a fashion and blended it with products which could help Indian customers, fill up gaps in their addresses. So unlike US or much of the developed world, when I was in US for an extended period of time before relocating back to India, I never realized how unstructured Indian addresses are. So unlike US, where you just put a street number, a flat number, city, and a zip code, and your address is complete. Trust me, in India, if you ask 5 people within the same family to write out an address, they'll all write different addresses. They'll add things like, landmark here, near this, above that, under this, and all sorts of explainable things get into an address, and which makes the problem very, very peculiar. So when Amazon came to India, we started off with a very similar construct of address validation, because it's extremely critical for us to validate address, how accurate it is, because the whole sorting process and going from all the way from middle mile to last mile, it's completely dependent on address. We still didn't have geocode based routing systems. Our routing systems are pretty much based on pin codes in India and local knowledge of the last mile delivery agents. So, it posed a very nice problem that, how do you really make sure that the address that the customer has given truly exists? there was no database to look up, and you can't just you can't just go to a post office like in the US, where you can just go to the post office and get the entire database of all valid addresses. India doesn't have a database like that. We had a company we were working with, Map My India. They didn't have a address database which is as extensive, and the customers were writing addresses in a very different style as compared to what the post office or Map My India had. So, the problem could not be a simple, I would say, a VLOOKUP kind of a problem where you could just hit against a database and figure out whether it's a valid address or not. So we realized that, there's a problem, we got to solve it. And we realized ML is the only way forward. So we constructed the problem in a way that, we start looking at joint probability of words. Whenever we are able to deliver a package in the first attempt, that is, assume that is the most accurate address. And then if there are certain phrases which are missing in this address text, that's what is missing. And hence we wanted to populate to the customers. And, okay, you know what, you are probably missing this. And hence we would like you to add. So I've just given you some examples. These are the kind of addresses people write in India. Sometimes it's completely fake, but the DA in India calls up before delivering. So you get the right address. And it's not a scalable process. Sometimes the PIN codes are incorrect. People in India we don't have boundaries like, the PIN code finishes here and the next PIN code begins here. Even in my apartment, half the apartment is on the other side of the road. So people use different PIN codes. And our sorting system just goes wonky when we have different PIN codes. Incomplete addresses, right? Sometimes people just write, I'm near a mall, just give me a call, I'll come there and pick it up. But it doesn't work like that. We have schedules to make. Each delivery agent has to deliver like 10 odd packages and so on. And plus, as we entered tier 2 and tier 3 cities in India, it became even more difficult because there were spelling errors, because our website was accepting only English, and these are mostly local language addresses. And a lot of the times when they were translating those local language addresses into English, it became even more difficult to interpret what is this address really. So that was the whole problem. And we kind of thought that this problem is more about figuring out which is a bad address. But instead of that, Amazon being such a customer-centric company, and our leaders said that instead of finding what is wrong with this address, help the customer and make sure that he adds that component to that address. And that's how we designed the entire program, ML framework. They were the same set of algorithms, but the whole orientation changed, and we kind of added more product initiatives around it. So if you could just move to the next slide. So the customer entered the address, it hit against an hash database. We used nearest neighborhood and nearest neighborhood and NER solutions to kind of break the address, pumped it into the graph-based neural networks, and then kind of brought up interpretable components of address which were missing, and how we could help the customer. So if you could please move to the next slide. So in this case, if you really look at it, the first address, if you enter an address like this on the India website of Amazon, the message will prompt, please complete or correct your address, because it is a non-existing existing address. It doesn't exist. If you were to add an address, which is on the second example, if the PIN code is incorrect, we populate, why is this this is the incorrect PIN code, here is the correct one. And we help the customer to accept the correct PIN code. Similarly, if they are missing a key component of the address, like in this case, Dr. Rajkumar Road, Malleshwaram was a very key string to complete this address. We ask the customers to add this particular string to the address so that we are able to, get it to the station which is located very close to this particular address. And lastly, a lot of times, people used to forget flat numbers and numbers in the address. But in our database, we saw that, whenever these addresses like these came, they had numbers. So we prompted customers that please add numbers and so on. So that's how we made it very, very explainable to the customer as to which component we were missing, and kind of had these product interventions to make the whole AI system more explainable and truly help the customer so that the address could be as accurate as possible, and they could get their deliveries on time. So it's a very different way of orientation of thinking about AI and just pivoting the problem on helping the customer rather than blocking the customer when the addresses are not correct.
Very interesting, Rohan. And so that's another interesting point, right? So you've introduced explainability to really enhance the customer experience as well. So rather than just saying, hey, you entered a bad address, correct it, you're actually adding in those explainability elements to point the customer to the right areas and help enhance the overall address base as well, I presume.
Yes, Arati. So very similar to what you had said in the earlier. So when I started back in financial industry, we used to give out reason codes. The concept is very similar. Here we're just giving out reason codes. Here are your reasons why your address is incorrect. So we just took that framework and kind of plumbed it with the deep learning neural networks that we have. Thank you.
Very cool. So from one COVID-19 related, a necessity to another, life sciences industry has gotten a lot of attention lately, and it's always been very important to our health. Anyways, we have Srayanta Mukherjee from Novartis, and AI is being used in very innovative ways in this industry, and again, explainability becomes critical in some of the applications. So Srayanta, can you talk to us about some of the problems that your team is working on, and where do you see explainability being the most important?
Sure, thanks Arati, and first of all, a big thanks for having me as a panelist. Guys, can I have the slides, please? Tech team, if you're here, can we have the slides, please? All right.
Go ahead. Yeah.
Maybe I share it myself.
Yeah, go ahead and share, Srayanta, if you're able to.
And let me know when you can see it.
Yes, we can.
All right, so I'm going to start off with a quote from our childhood, from Alice in Wonderland. You see, the adventure sometimes is so exciting that who cares about the explanation, right? And that, I think, sometimes is the crux of the problem. We got so involved in making this new architecture that we forgot we can't understand what the architecture is doing. Right now, in healthcare or life sciences, like in a company like Novartis, when we are using traditional AI pipelines, very likely it's going to affect patient lives, right? So the criticality of explaining something becomes very, very important, extremely important, in fact, right? Now, so imagine a doctor sitting there and you're saying, here's a prediction that our AI algorithm has made. The doctor is going to be like, really, can I trust this, right? Because we are, again, dealing with patient lives in the pharma industry, right? Now, just like if I make a statement that, look, I grew these potatoes on Mars, you're not going to believe me because I have no way of explaining how I grew those potatoes on Mars. Similarly, if a machine makes a prediction, and trust me, machines can sometimes are so powerful that the prediction looks incredulous. Why should we trust it if it is not explainable, right? That, I think, is the crux of the problem. See, it's not magic. There's no Harry Potter at work in any of these machines, right? It's this triumvirate of geometry, optimization, and linear algebra. But it's very difficult sometimes to explain that in hyperdimensional space, your words or images are embedded somewhere, right? And here's how it's looking. Sometimes we can't even track that, right? If you're doing a TSD plot, we are ultimately losing all the dimensionality and putting it in 2 dimensions, right? So the crux of the problem is, can we overlay something on this triumvirate of, geometry, optimization, and algebra so that it becomes much more explainable to the layman, right? I think that's the problem we are discussing today. And what we at the pharma industry or the life sciences industry are big on is, first of all, trust. That's the main problem, right? Can we trust because it's patient lives? Causality is something that is very important again, because, biology or the human body itself is a black box. We know very little about the human body. And if we are making the problem worse by putting another black box to predict about the black box, it's a mess. So many of the things that we are doing, especially starts with semantics and visualization, right? Especially at Novartis and in many other pharma companies, actually. Semantics and visualization play a big role. And if I can explain that with this example, not from the life sciences per se, but traditional object detection will look at this image and basically say, oh, there's a tunnel and there is a railway and there is a boulder. All right. And in the anomaly detection sense, it will probably detect as an anomaly the way the boulder is placed and say there's something wrong. Now imagine a real man standing there and he gets, okay, I got a boulder and a railway track and a tunnel. Do something about it. He'll be like, why? But then if I overlay semantics on top of it, right? Especially like this, that, okay, there is this train operating on this railway track and it's currently getting obstructed by this boulder. So if we semantically link many of these things, suddenly it becomes explainable. Imagine again in the life sciences context that somebody goes to a doctor. The data basically says that somebody went to a doctor and he was diagnosed with a cough and a fever, and he was prescribed a Benadryl and a paracetamol. Traditional AI will basically say, okay, cough, fever, Benadryl, paracetamol, all are related. The reality is the Benadryl was prescribed for the cough and the paracetamol for the fever, right? So if we can semantically link this thing, we start explaining a lot of stuff. And that's a big focus, I think, in the life sciences industry. So if we have, for example, a connected knowledge graph of clinical trials, can it help unleash causalities of operational successes and failures? If we again have a connected knowledge graph of biomedical literature, imagine the structured learning and the understanding we can get about it, right? An enterprise-wide search algorithm, semantically linked, right? So that, for a large company, it's very important sometimes that, somebody's doing something if it's exactly same to somebody else is doing. And again, pharma has a big role to play with optimization of manufacturing and supply chains and all that. Semantic technologies also play a big role in making the pharma manufacturing and supply chain very efficient. I think, Arati, that's what I have from this side, but semantic technologies, I think, is the way to go.
Thank you, Srayanta. Yes, definitely an interesting new field. Again, this is an interesting one where ontologies have been existing now for so many years, but this whole technology is getting a new lease of life, and I think knowledge graphs and semantics are going to evolve and add to the sophistication that we are building into the AI systems. So from industry, we'll move to academics now. Professor Vineeth, I know your team is doing a lot of work in explainable AI. So if you could talk about some of the work as well as shed some light on how academia is contributing to advancing this new area.
Sure. Thank you, Arati. And thank you to the organizers for having me here, and also the other panelists for sharing very interesting perspectives. So I'll just take a few minutes to share an academic perspective to these issues. I do think there's Professor Dietrich coming on later. I'm sure he'll have a lot of deep insights to share, but let me share it in my own little way. So obviously the academic community has been doing a significant amount of work in this space over the last few years. As Rushi mentioned, one of the acronyms people use here is FATE: fairness, accountability, transparency, and ethics. And these are 4 different dimensions in which there has been a lot of work going on over the last few years. In fact, ACM now has a conference. It used to be called FATSTAR. Now it's called FACT. It stands for Fairness, Accountability, and Transparency. In fact, the deadline is tomorrow. So I think there is a lot of interaction between ML scientists, AI scientists, as well as social scientists to be able to study these perspectives in the same platform. I think this is something that traditional AI machine learning conferences don't study that confluence. And I think now we have an avenue to be able to study this together through these series of conferences. And this has been active over the last few years. So just a bird's level view of what is being done in explainability broadly. So I think broadly people have looked at methods in explainability as post hoc or anti hoc. I think on one hand, you have post hoc methods which are easy to develop. So you already have a machine learning model and you add a layer of explainability on top of it. I think that's what most models do today. Most methods that people do for explainable AI, you add a meta layer around a machine learning model, whatever it be, support vector machines, neural networks, whatever it be, you add some layer around it and then deploy that system. While that is good, that has its own limitations. On the other hand, anti-hoc models such as decision trees are where the interpretability is actually built into the system. Obviously, we don't have good ones with neural networks today, where the explainability is baked into the training of the model itself. That's something that needs a lot of effort as we go forward. Then you also have model agnostic methods where you have explainable methods independent of what's the base machine learning algorithm. Then you have model dependent methods which rely on a particular architecture, a particular kind of an approach. Then you also have global methods. I think to some extent, this again talks back to Rishi's point about methods that can give explanations at the level of a population, or local methods that give explanations at the level of every instance that's provided. So today you do have all these kinds of methods, but of course it's nascent and still in the phase of development at this time. And in terms of, I'm quite sure most of us here are aware, I think the perspectives are to study feature importance in some way using partial dependence plots, individual conditional expectations. The popular methods here are LIME, LRP, deep lift, integrated gradients, SHAP, deep SHAP, so on and so forth. I'm not going to go into each of them here, but let me take a few minutes, probably just to, probably not few minutes, just a minute more, perhaps just to talk about some of the efforts that we have ongoing at IIT Hyderabad. So one of the things we've been looking at is how do you integrate causality into machine learning models? Again, I think this goes back to a couple of earlier panelists who also mentioned this. We've also been looking at visual explanations in images. Lan mentioned this earlier in her talk too. We're also looking at trying to see how do you bring common sense reasoning into these models. I think AI/ML is broadly data-driven, but human decision-making is not necessarily data-driven. There's background knowledge, there are ontologies, there are knowledge graphs that all influence the way we go about thinking and making a decision. So how do you integrate these into machine learning models? And finally, we've also been looking at the intersection of explainability and adversarial robustness. I think adversarial attacks, especially from a security perspective, have been an important topic today. And there are lots of connections between the two, because I think if you can explain a decision properly, then it's not possible that a simple pixel perturbation can give a completely different outcome, and you can even explain that perturbed outcome in a sane way. It's just not possible. So the explanations can regularize how you deal with these. So we had developed a method called GradCam++, which is actually being used today for finding defective cells in solar arrays. And going back to the point of COVID, our method has actually been used for COVID detection in X-ray images to be able to explain the decision, to find out which pixels are responsible for that particular decision. We've also been looking at introducing a machine-generated rationale for an answer. So if you have a scene and somebody asks a question on that scene, why is so-and-so hiding his or her face? An answer is generated, which I think we all know NLP can do. But we're also talking about generating a rationale, human understandable rationale, to say why that answer was given. So this part of it is still new, and it involves a confluence of vision, NLP, and of course, core machine learning techniques. We've also looked at causal attributions in neural networks. How do you ensure? Of course, deep neural networks are fundamentally correlation based. They learn the correlations between data and come up with predictions. And it's obviously that, again, Srayanta also mentioned this, that the correlations need not necessarily cause a particular outcome. How do you disentangle the correlations in data and the causal relationships in data? So we already have a method which is derived from first principles that can, the code is available in fact, which can be used for, given a trained neural network model, how do you find out what causal relationships it has learned from first principles? This is something that we have done too. And obviously, we are not the only group. There are lots of efforts going on. I think many institutions around the country, as well as industry in the country, have been looking at fairness, explainability, detecting fake news, deep fakes. All of those efforts are also going on at this time. I'll just conclude with a few questions here. Is what needs to be done? I think the fundamental formalizations of AI/ML are based on an input and output, an X and a Y. That's how the entire formalizations of ML are made. But currently, we are asking these formalizations to also give a Y hat, which is an explanation, right? An output is no more just a prediction, but has to also give an explanation. So how do you revisit fundamental formalizations to keep in mind these kinds of output spaces? How do you balance the trade-offs? I think it's a known fact now that if you focus too much on interpretability or fairness, your model can get less accurate. So how do you balance this trade-off? And an important elephant in the room is how do you evaluate explanation systems? I think we don't have data sets. Once again, going back to the first point, our data sets are XY driven, right? Input and output. So when you don't have an expected explanation, then how do you evaluate explainable systems becomes a huge problem. And when you have post hoc explainable methods, where you add a layer of explainability to machine learning models, who owns the explanation? Suppose you give a wrong explanation, was the model wrong? Or was the explainability method wrong, right? That again supports the need for anti-hoc methods in machine learning, where the explanation is also baked into the learning itself. And just a last point there is that I think it's a nice opportunity to bring together symbolic and connectionist AI. Historically, they've been seen as two divergent paths, but I think connectionist AI, like neural networks, and bringing in logic from symbolic AI could be a nice marriage to be able to predict as well as have a logical rationale for those predictions. I'll stop there. Thank you again for the opportunity to share thoughts.
Thank you so much. Very, very fascinating. And I think if one thing is clear, that is that explainability is not a simple topic by any means and has so many different layers and dimensions to it. So my next question is to Dr. Anand Rao. Related to how should then organizations or teams think about incorporating explainability in their AI strategy? What are some of the pointers that you would give to folks who are looking to incorporate explainability?
Yeah, thank you, Arati. Yeah, again, thanks the RAISE committee and the esteemed panel here. Very glad to be on this panel. So as you asked, so what do enterprises really need? What do companies really need in terms of explainable AI is what I wanted to tackle. I want to drive home just 3 key points here. I know we have been focused very much on explainable AI. I think we did started with the bias. So when we look at explainable AI, it should be, especially for enterprises, it is just one part of a much broader solutions. There is a number of different issues from safety, robustness, and so on. And explainable AI is one part. I think we need to realize that, recognize that. Then I want to go into what are some of the components of explainable AI. And then finally, I'll tackle something around how do we just balance it with other metrics. Again, goes back to the first point that it is explainable AI is just one part of a bigger story. Now, what is that story and why do we even need these kinds of things for enterprises? Now, I want to take you into a world where we are not the policymakers, we are not in the academic field. There are companies using AI today. So now this is what we have from a policy perspective, right? So there have been more than 100 plus organizations releasing AI ethics literally over the past 3 years. Now, this is a very good guideline from European Commission on trustworthy AI. So basically, we get some of these kinds of principles, very valid principles of explicability and operating transparently. Again, I'm not going to read through this. You can see these are words, again, very thoughtfully come up with these words, right? So being part of some of these committees, we spend enormous amount of time trying to define and come up with these principles. So in that sense, I think the community has done a great job. But now, if I am an executive in a bank, in a healthcare company, this doesn't tell me what do I need to do to even check for explainability and check for explainable AI that my team is building. And the team also looks at this and says, yeah, I understand this, but so what? Where do I go from here? So we are trying to bridge the gap between the policy world, the academic world, and then really see what are some of the things that needs to be brought together, not going into too much of detail, but raise it so there are people with sufficient level of expertise who can go into the detail. So that's why over the past 5 years, we have been working in this model and expanding in this model, which we call the Responsible AI Framework, released, I think, in 2016. And if you look at this, it's not all technical. So the whole explainable AI, responsible AI is what's being called now as a socio-technical system, right? So people are very much a part of it. Now, in the middle, you see a few boxes there: bias and fairness, explainability is there. Again, as the speakers have pointed out, interpretability, explainability go hand in hand. One is with respect to all models, explainability is with respect to specific examples, robustness, security, safety, privacy. We can go on, right? So, and there are a number of academic work in this area. So all this is very technical work, which the data scientists, AI scientists are doing. But this needs to be wrapped up, and all this is happening within a much broader context. It's happening within the context of the ethics and regulation. Not everything has become regulation. Not everything may become regulation either. But there are certain things that we as good companies should follow. As society, we should follow. That's all coming in. Again, lots of work on the ethics and regulation, but needs to be embedded and contextualized with all of these technical domains here. And then on the other hand, you have governance, risk, control. And we started off with a beautiful example of the ICBM, right? So that happens with all the governance that needs to be in place as to who is checking some of these things. Things can always go wrong, and then you need to prevent from going wrong. And that's where humans have played, and humans should still play that role. So this is the overall responsible AI framework. Now I want to just dive deeper into just that middle box there around explainable AI. And again, I won't go into what is explainable AI. I think a number of speakers before have talked about it. This is the slide which essentially adds that explainable layer, which DARPA released, and that's what I would say has sort of given rise to this whole rich research. Now, when we look at explainable AI, explain to whom? Why do we need to explain? How to explain? What are the explanation techniques? All these things are things that people need to be aware from within the enterprise. So now what do we mean by whom? Now, there's a number of different stakeholders, and the explanations have to be very different. There's a business sponsor, right? So I'm a CEO, I'm a CFO. I'm not concerned about the exact detail about what the model said. How did you balance fairness and accuracy? I just trust my people, but how do I make sure that trust is valid, right? So what are some of the risks? Are there people, processes, procedures that people are tracking with respect to explainability? I obviously don't want to be exposed, don't want to be on Wall Street Journal top page with respect to my company. Then there are regulators. Regulators come in many areas looking at the models, and their issue is very much, hey, can we make sure that these things are not harming humans? They are obeying some of the regulations. Similarly, end users are people, they don't care about whether you use the most sophisticated neural network or a very simple regression. They don't care about it. I just didn't get my loan. Just tell me what I should do to get the loan, right? So it's a very simple, but again, the explanation needs to be very much actionable to them. So end user explanations are very different. And on the other hand, the data scientists, as I think we just went through and Vineeth just went through, we want to go into the details, right? So how did the neural network actually make that choice? And can we have a neural net explain another neural net, right? So we are very much in that technical side. So I think explaining to whom is very much needed here. And it's not that it's just one or the other. In an organization, you need all of these, right? So at various points, you need all of these explanations. And that goes into why explain, right? So the objective of the explanation, not just to the whom. So the objective obviously ties very closely to whom you're explaining. As I said, reputational risk, corporate governance for the business sponsor, consumer harm or compliance for the regulator, or actionability, trustworthiness. How do I even trust the system? Trust my bank's AI algorithm? And all of those things is what I think we need to say. Why are we explaining this? So these are just two aspects. So now when I go into how to explain, I wanted to just take a very simple example that we had done. This was an insurance company where all of these photographs are coming into them, and essentially humans were originally looking at these and then assessing the risk. Is it a total write-off? Is it, what type of a damage is this to the vehicle? Now, this project, I'll just show you what are the different types of explanation one can give. And I think some of the panelists earlier had talked about how you need to be very visual, right? So the same explanation, I'll try and show it in very different ways here that we implemented. So it's a simple fender bender or bumper mistake that you have seen there, crash. Now you can explain it graphically. Now, what is the scratch? There's a scratch here, there is a dent, there is a crack. All of these things are being explained, but visually. So the system is highlighting with a heat map, and the more darker it is, then the more dent there is or more scratch there is. So this is a good way for even a layperson, but also this is a way I think the special investigation unit tries to look at it and then tries to zoom into some of those areas to get a deeper explanation. So that's one way of looking at it. Another one is a natural language explanation. So some of these things we were doing, and obviously sending the graphical explanation, but also sending a natural language explanation. So this says, this report is generated from this claim ID, and we determined that these are the variables involved, and there are several parts that are damaged, and we think it is a bumper that needs replacing with 75% confident, blah, 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 right? So there's a whole natural language description. So anyone reading that says, okay, so yeah, I can see that. So that's natural language explanation. And then you can go very technical neural network and then start saying, hey, if it's a dent, what are all the things that fired here to be able to say why it is a dent? Is the system actually working properly? Is it distinguishing a scratch and a dent appropriately, right? So you can go into all of those. So that's again for the technical people to build in and to analyze the system. Or it could be more structured, right? So basically giving various probabilities and confidence levels on the various parts. And that's something that, again, experts can go back. So this is where the experts in the crash domain or the insurance domain are working with the data science domain, right? So that is sort of more understandable to them as opposed to either a graphical one, which may not go into all of the details, or a natural language one might miss some of those. So you need a combination of all of these things to explain. And finally, I want to just look at what are the explanation techniques. I think Vineeth just went through, and some of the previous speakers went through. There's a whole host of those. So now this is just a paper from this particular source, and it talks about text explanations. How do you simplify the model? How do you visualize? How do you give local explanations? There are a number of these things. So now, again, if I'm sitting in a company, I need to worry about all of those things, or we want to make sure that different people at different levels understand these various components. So the data scientists are doing their job with understanding all of those different techniques. There are tools that they can use that make it easier. The FAT conferences are great, but there's been 5, 6 of those conferences with, I don't know, roughly 80, 100 papers. A person who is doing a day-to-day job is not going to read the 500 papers, right? So what is relevant for them? So all those things need to come up. So you really need to bridge what's happening in the academic world, some great work, with what the policymakers are requesting us. Again, just want to close by saying this is a multidimensional trade-off, right? So we just looked at explainability, and that is just one axis here. And I just put bias or fairness on the other one. There are 35 mathematical definitions of fairness, and how do I know which fairness definition I've chosen, and how do you rate me on that fairness versus performance? So data scientists have typically looked at performance, and that's all they care about. But now, of course, with all the responsible AI, they're changing their mindset that this is a holistic problem that needs to be balanced with multiple things. Again, we can use the math, we can use all of the technology, but we also need to raise it to a level where others and enterprises can understand. So that's where I think we think the push should be to how do we marry the policy making with the academic work and present something to the enterprises in an easy, understandable way in terms of frameworks and tools and so on. So that let me stop.
Thank you so much, Dr. Anand. And again, very interesting points. I think the explain to whom is a very pertinent point, because the type of explanation will change depending on what you want to get out of it and who the stakeholder is. And that's an interesting aspect.
A little bit about the history of the subject, because it helps set the stage for explainability. When I was a graduate student in the 1990s, one of the areas where I worked was building expert systems, the previous generation of AI, but also neural networks existed even then. And they were an interesting but not practical area. Why did it change? Of course, neural networks evolved to become machine learning based artificial intelligence, but it's also true that the technology evolved and became much more powerful. Without the foundational technology development and especially computing power, we would not have the artificial intelligence that we have today, even though this is an emerging technology with a lot of innovation in it. It's probably interesting to know that more than 90% of artificial intelligence systems run on conventional processors, and they also use conventional software principles. So we are looking at something that already existed. We perfected it. Computing power made processing techniques that were impossible 20 years ago possible now. And here we have this new generation of artificial intelligence. We learned a lot of things along the way, and they have pertinence for explainability, just like they have pertinence for everything else. One of the things that we learned is that imitating the brain is not always optimal. In fact, computers perform many tasks much better than humans. Human decision-making is not always data-driven. We use different techniques to distinguish, I don't know, a cat from a dog in a set of pictures, but we want to explain what we have done to humans using the power and the abilities of the human brain. So that creates the first difficulty in how we address explainability. The second is connected to the first. We do not need to imitate the human brain, although we need to know how it operates. And we need to rely on formal parameters, structure, and syntax more than semantics, at least at this point. So let's see. Can you see the next slide?
No, not yet.
Not yet.
Okay, I'm trying to.
Yeah, unshare and reshare.
Yeah, here we go.
Yeah, we go.
So let's set the stage for explainable AI. Everyone knows the definition. What we are talking about is that the power of computing that goes to artificial intelligence can be understood by humans. But there are many areas there that are not straightforward. AI systems exceed human performance for many tasks, but the explanation that is required has to be presented in human terms so that humans could trust the systems. This is a legitimate requirement, but it's not as straightforward as it appears, because the technical definition of trust, expectation that a system will perform in the same fashion under the same circumstances, is not sufficient for explainable AI. We don't only need to have a repeated predictable performance, we also need to have an explanation that could be consumed by humans. So as a result, a new term, trustworthiness, AI trustworthiness, was coined in a new system of principles, explainable, for explainable, transparent AI, usually referred to as responsible and ethical artificial intelligence, was coined. And this, in the technical sense, are not the same. We need to also know that transparency, which is a desirable feature of artificial intelligence systems, is not the same as explainability. They may be connected under many circumstances, but they are not the same. And finally, as we moved from rule-based systems to machine learning-based systems and artificial intelligence as the foundation of this field, we came to understand this trade-off between explainability and accuracy. Systems that are based on machine learning build their models automatically. Those models lead to results that are more extensive. They are more accurate, and the models are extremely complex. But because of this complexity, because of the machine-generated code, they are much less explainable. Older AI paradigms, paradoxically, that are handcrafted, where the rules are created by humans, the expertise is codified by humans, is much more explainable, but of course it's much less accurate and frequently much less efficient. So another thing to understand about explainable AI is that the explanations are, as was already stated by many speakers here, not always simple and sometimes quite extensive, even for the lay audience. When I went through papers and slides on explainability, the example usually given for explainability is how does an artificial intelligence system decide that this image is a cat? Well, this is a simple question. It can be explained in simple terms. And the model for the explanation is easy to understand. But the real questions in decision-making systems are much more complex. Why should you build a factory in this location? Why the weather system that is forming over the Atlantic is a hurricane or might become a hurricane? Why this chemical compound is optimal for treating this illness. So those are much more complex decision-making problems requiring multiple parameters. The explanation is always audience-dependent, it's problem-dependent. So what we established here is the greater computer power, the more complex the processing, the more machine dependent the model is, and the harder it is to create an explanation that can be consumed reliably by humans. So what can we do? Well, we can put an onus on the system developers. Many companies, including Intel, have adopted principles of ethical and responsible AI for the development of artificial intelligence systems. This will go a long way towards engendering trust in the systems, although it will still be difficult to get explanations for all the decisions taken by computers. We could develop sophisticated testing to further engender trust, testing artificial intelligence systems in a way that really demonstrates what they do and how they do it. In a way similar that is done for security, for instance, will continue to remain an ideal goal. We need to understand the role of transparency in the big picture. Sometimes it helps the explanation. Sometimes it is as important. And finally, although it could have come first, we need to develop novel explainability mechanisms, something that will work with different audiences, different machine-generated models, and in different circumstances. There are already many methodologies to do this. None of them work in 100% of cases, but I think we will arrive where we have techniques that work much better. We just need a little bit more time. Thank you so much.
Thanks, Claire. Yes, and you know what you said about sort of the human brain and we don't need to replicate that. But one of the things that has always fascinated me about explainability is we have not demanded as much explainability from human experts as we now demand from AI systems. And that's also one of the reasons that this is something that we are still working through, how to build these explainability mechanisms. I'll turn next to Professor Dietrich. We've talked we've had several examples on supervised models and training models on various applications and building explainability. But you've done a lot of work on anomaly detection and unsupervised learning and how to develop explainability in those scenarios. So please give us some insight into that area as well.
Well, thank you very much. So it's been wonderful listening to all of these presentations. And I think you brought out many of the points that I also was thinking of talking about. So I'm just going to focus on, I guess, the key issue with anomaly detection type problems is that, of course, we have no training data that tells us the right answer. So typically, I'm interested in problems like, say, fraud detection in financial transactions, credit card transactions, or perhaps cybersecurity problems, and also problems in the Internet of Things. So I'm involved in a large effort called TAMO, the Trans-African Hydrometeorological Observatory, which seeks to deploy and operate a network of automated weather stations throughout all of sub-Saharan Africa. And of course, this is a classic kind of Internet of Things application. Each weather station has a thermometer and rain gauge and wind speed and direction measurements and so on. But of course, because these instruments are put out in the weather, they break, they get dirty, and we need to discover those. And so we look for inconsistent or unusual readings coming out of the sensors. Of course, a theme that has come up today is that there is always a who is the customer, who's going to be looking at these explanations. It's not enough, of course, for the system to just say, this is here's an anomaly, this looks strange to me. You need to explain to the user why. And in this case, the user is typically say a fraud investigator in a bank, for example, who is going to look at this anomaly and decide, do I need to open an investigation on this case, or is this just a false alarm? Because another overwhelming problem in anomaly detection is we get a lot of false alarms. We're using only statistical patterns to find things. And of course, when the real world exhibits change in the trend is strange. So it can be heat maps and time series plots and so on. And people have brought out the point that there is no one standard explanation. It depends critically on the application and the larger problem setting. I thought the point of going beyond the XY mapping to think about the larger problem and how we formalize that is a great insight, and that I hadn't heard explained so clearly. So so we develop systems that, of course, give that explanation. And then a beautiful thing is that this analyst can tell us, yes, this is a real alarm, I need to investigate, or no, that's a false alarm. And there we get useful feedback. And so we find we need to do online learning then, and we can go from a system that perhaps detects only 20 true alarms out of 100 alarms to one that can achieve, say, 70 true alarms out of 100 by being able to very rapidly incorporate the feedback during those 100 alarms as we're presenting them. We're able to tune the anomaly detector.
He was quite bitter about it, Kasparov, but later on, if you look at IBM Watson beating the Jeopardy masters, and more recently the Google AlphaGo versus Lee Sedol, which was he got beaten 4-1. But the question, of course, is at what cost? So some of these high performance machines, they probably need about 200,000 to 300,000 watts, and the brain possibly does it at about 20 watts or so. So there's a huge energy efficiency gap. So on the other side of it, if you're to really look at, for example, edge applications, and we took an example of a case study of object recognition in a smart glass with the state-of-the-art accelerator as an example, and which is taking the Google TPU, where I'm showing flight attendant recognizing, sort of using this glass, their good customers and providing them in a customized service. Turns out if I were to really implement that in a RetinaNet DNN on a smart glass, and without going into any details of it, turns out that the battery life under ideal conditions is going to be about an hour. And that's, again, not sustainable, because under real conditions, it's probably going to be half an hour or so. So the question, of course, is where do these inefficiencies come from? It comes from the algorithms. I mean, we certainly don't know the exact algorithms in the brain. The hardware architecture, to tell you the truth, the hardware architecture that we still end up using are very much like the standard von Neumann machines. But from whatever little that we know of the brain doesn't really have a processing unit on one side and the computing unit, the memory on the other side. So it's all mixed together in a lot of ways and doing computing in the memory itself. And then certainly we don't have the right kind of circuits and devices, meaning thereby I don't have directly the neurons and synapses of the brain. But there are a few other things, and as you all have been talking about, it's not just the compute efficiency. There are a few other things that are also very, very important. Today we need a humongous amount of data to learn. So question is, can I learn with less data? That turns out to be quite important. Another issue, and to a certain extent, we were talking about it earlier, is generalization and robustness. So if my system, for example, my AI learns this to be a chair, the question, of course, is, are these to be considered chairs? There's a lot of things that you need to consider, not just the features, but the context and so on. And, we talked in the panel discussion, you talked a little bit about this adversarial robustness. So it turns out the robustness is as a real problem. If I take this macaw as an example and I multiply that with if I add some, crafted noise to it, to a human eye, it still looks like a macaw, but my system in this particular case, it's a bookcase. So that's another problem. And finally, can I do incremental learning? Turns out that today's system, if you learn a particular task 1, followed by task 2, followed by task 3, you'll probably end up forgetting task 1. But we humans are pretty good at, in some ways, lifelong learning, right? So the question, of course, is, can I really, rather than mixing all these tasks together, do an incremental learning in that fashion? So with these inefficiencies, I'm going to go back and talk a little bit more about the workloads. The AI workload is certainly changing. So today we are talking about the standard convolutional neural networks, so the recurrent neural networks. There's a good amount of talk on this graphical neural networks or memory augmented neural networks. So, and going further, going towards, today's panel, which is causal and explainable AI, right? And if I were to look at the hardware today, and these are the GPUs and the accelerators, they are targeted towards today's algorithms. And we are moving towards doing better, vector matrix multiplication, doing in-memory computing and so on. But it's still a huge, not only a functional gap, but there's an energy efficiency gap that lies today. So with that in mind, the question, of course, is, can we take cues from the brain? A little more cues from the brain. It's the standard artificial neural networks certainly are brain inspired, but can we do a little bit better because we have an existential proof that brain is efficient? So the question then becomes, what kind of neuron models should I use? If you look at today's deep learning, mostly it's using ReLU or maybe TANH kind of activation. But more importantly, can I really take a Hodgkin-Huxley model or a discrete leaky integrate and fire neuron, which are more brain inspired? And what are the advantages if I do that? Can I do better generalization? Can I actually have better energy efficiency? Can I use a right kind of learning algorithm? Today we're mainly using a backpropagation based learning, which is sort of an optimization. But the hippocampus of rats, you've noticed basically, spike timing dependent plasticity, based sort of localized learning. So can I use that in some ways for better training efficiency? or maybe a combination of these. Now, what kind of network topology should I use? Should I use long range connections? Should I use feedback connections? And finally, there's something very, very important and interesting is that, the hardware that we're going to be talking about, and the hardware development is absolutely important. So the question then becomes, hey, should I have computing and the communications with spikes? And that's sort of getting closer to what the brain does. Should I have an integrated compute and memory? Should I do asynchronous event-driven computation? And finally, what kind of input coding should I use? Should I use rate-based coding? Should I use the time-based coding? Should I use, for example, for these images as an example, should I use DVS cameras? And I'll talk about that DVS camera in just a minute. But what are the possibilities? So with that in mind, one can look at neuro-inspired algorithms, and I'll briefly talk about some of these. Can I do bioplausible learning, where the bioplausibility can come from having a network architecture, which is similar to what the visual ventral system is, as an example. Should I do brain-like information representation? That could be, as an example, in the form of spikes or a mix of spikes and other kinds of information representation. Should I be able to do, in what way should I do lifelong learning? We talked a little bit about in the panel, the theory and the AI being the black box, right? So there's a need for theoretical understanding so that I can have better generalization, explainability. And at the end of it, of course, other kinds of robustness like adversarial robustness. And finally, it turns out it's also important that the algorithms that we develop sort of do have the hardware in the loop, so to say. And if I do that, that's the possibility of getting a good amount of energy improvement. So with that in mind, one can certainly look at bioplausible neural network architectures, and this is something that I'm showing. It's actually done as a part of in our center. DeCarlo's group at MIT is looking at the visual ventral system, which is shown at the bottom of a monkey brain. They're doing measurements, and based on those measurements, they're trying to look at different kinds of networks, which are shown at the top, and these networks really are trying to figure out, hey, which has a better quote unquote brain match? Or can I give a brain score to it? And if I do have a better brain score, so to say, then do I have a better network? Do I have better robustness? And to that effect, the results are quite interesting that the brain-like networks indeed seem to be more robust. On the other side of it, can I do brain-like information representation? And today's most of deep learning is actually using, as an example, the standard sensors and standard inputs coming from the cameras. However, there are different possibilities. If I were to really look at, for example, an optical flow, there are event-driven cameras, and these cameras are kind of interesting, and they actually provide spike outputs. So if there's a relative motion between the camera and the object, then spikes are produced. Else, there is not going to be any spikes. So in other words, these are very energy efficient cameras. So with that in mind, since these are spikes, is it possible that I build networks? And I'm not going to go into the details of it. Training these kind of networks is quite interesting and time consuming in some ways, but because of the spikes, but because of the hardware architecture, are not certainly suitable for that. But one can potentially think of a network with a front end is an SNN, which is a spiking neural network, which picks spikes coming from the cameras. The back end, for reasons of accuracy, becomes an ANN. So it's a combination of a hybrid neural network, which does spiking and analog computation in some ways. And this is an example of doing, for example, real-time flow prediction using these networks. So turns out that this is my student working in front of the DVS camera, getting a little bit of exercise. But what I'd really like to show is that the spike image on the left and the masked predicted flow on the right. Few other things, they can actually do gesture recognition and within these cameras, and using networks which are again spike based. In this particular case, a liquid state machine, which is a random connections of these neurons in some interesting ways, and very small network. And in this particular case, you can train this network. For example, my student is actually doing a DVS camera based asking the robot or commanding the robot to, or in this case, a drone to go up, go down based on these inputs that are coming in. I'm going to skip that, but you know, you can do various things, going forward, we can also do different kinds of lifelong learning. And as I mentioned, you know, what is continual or lifelong learning? Today, you know, we are certainly, and the brain is certainly very good at doing that, but you know, the neural networks are very, very efficient too. If I were to really say that, hey, can I distinguish between a cat and a dog? And it does a really good job. On the other side of it, my new task, let's say if it's a bird versus flower, certainly, you know, task 2, our network, you know, the brain does it well, the network does it well. But if I now end up showing, you know, after that, a bird, my network, the neural network does pretty well. But when I show a dog, I might have forgotten, my neural network might have forgotten, but the brain certainly doesn't. So this is actually called catastrophic forgetting. So with that in mind, is it possible to actually now build networks which are sort of, you know, more quote unquote brain-like, and we continually learn and forget things which we need to forget. So to that effect, you know, there are various possibilities. One can actually, you know, design networks having a core area and a residual area. You learn, you know, don't change things in the core area as you keep on, you know, having new tasks coming in. You grow the core area, and the residual area actually sort of decreases. But the core area, you don't change. And it turns out if you do that, there's some, you know, you don't end up forgetting, you end up learning, but there's a need for, you know, some task hints and so on. So there are different interesting possibilities on this domain too, utilizing the network capacity efficiently to overcome, you know, catastrophic forgetting and learning in a hardware-friendly way. And finally, you know, I'd like to end with a little bit of work, you know, interesting work. It's farther, you know, there's a long way to go. Can we really look at some of these emerging hardware? And I know that, you know, some of you may not be in that area, but what I really wanted to show is that, you know, we are talking about neurons and synapses, right? And I'm showing a huge number of these, you know, interesting devices which are not standard transistors or CMOS-like devices, right? These are spin devices or memristive kind of devices, which have some very interesting properties. And these properties are, you know, they're colorful in their own ways, but their properties are that they actually have a behavior like a neuron, or a synapse, directly implementing that. So as an example, if I to really look at this, you know, standard biological spiking neuron, which has these input spikes coming in the membrane potential going up like that, and then, you know, producing a spike. Turns out that if I were to really take one of those devices that I shown, one of those you know, magnetic devices that I shown, and one can show that the magnetization dynamics, which is shown by these, you know, a little bit complicated equation over there, turns out it actually, the magnetization dynamics really behaves like a spiking neuron. So if, you know, can I use this device directly? So those are the interesting questions. And it turns out you can use these devices directly in sort of, you know, spiking neural networks, or it could be actually a standard, you know, ANN also to have, you know, programmable synapses on one side and the neurons on the other side. You can put these things together into an interesting architecture. Can be done with standard CMOS too, but more efficiently with these devices. And that can potentially give you, you know, good results and interesting results. So I'm not going to go into that, but it's possible to get a good amount of improvement, about, you know, 10 to 100x improvement over today's, you know, CMOS-based computation. So I know that I've gone a little fast, but you know, at the end, what I'd like to say is that in conclusion, I believe that bioplausible and spike-based information representation today at this point can potentially give you robustness and energy efficiency. It's certainly potential for edge computing, where you can potentially also do training and inference with these DVS cameras as inputs. And I also believe that you know, research in these emerging devices can potentially harness the spiking and the synapse and the neuron functionalities. One of the things that we have not really been able to effectively or very effectively use the temporal domain. information when we're using spikes. So, if you're able to do that very effectively, then potentially we can learn better. So with that in mind, I'm going to end and say that, hey, the algorithm hardware co-design guided by biological principles can potentially be a pathway for the next generation neural computing.
Thank you, Vishik. Go ahead, Dr. Sanjay.
Yeah, I think this has been a fabulous session by Professor Kaushik Roy. Personally, for me, I can say that throughout this session, moderated by Arati and all the distinguished panelists, and then, of course, started by Lan and ending by Kaushik, it's been a complete learning experience for me. I've learned a lot, and I'm sure all the people who've been on this session would have benefited and are going to definitely take back a lot of dimensions and points which they will be using as they move forward in their areas of AI that they are working on or plan to work on. With that, I would like to thank each and every one of you for putting in that effort and sparing your time, valuable time at this RAISE 2020 and making this wonderful hot topic, a complex topic, so lucid for everyone to understand. And also thanks to Lan for starting it and Kaushik for ending it, and then moderated in between by Arati and all the panelists in between. Thank you very much.
Thank you. My personal thanks to all the panelists as well. Thank you for your time and your insights.
Bye-bye.